Hey everyone, and welcome to this explainer. I'm so pumped you're here today because we're taking a deep dive into one of the most critical yet totally underappreciated marvels of modern engineering, the electrical transformer. Whether you're an engineering student, a seasoned MEP pro, or honestly just someone curious about how the world works, our goal today is to completely unpack how these silent machines are classified, how their internal anatomy actually functions, and how they seamlessly hook into our global power grid.
So just think about this for a second. We generate electricity at these massive power plants, right? And they're often hundreds of miles away from the cities that actually need the power. How on earth does that electrical energy travel such insane distances without just burning up all its energy as heat along the wires? Well, the answer lies in the ultimate engineering workaround, the transformer. It's basically the gatekeeper that makes our entire modern connected world possible.
All right, let's dive right into this. Here is our syllabus for today. We'll cover the physics of power, step-up versus step-down types, transformer anatomy, efficiency and losses, and finally, the big picture. This Section 1, the physics of power. Let's start with the absolute basics. What exactly is a transformer? Basically, it's a static electrical device, which simply means it has literally no moving parts. It uses this really cool principle called electromagnetic induction to change voltage levels. But here is the absolute golden rule you have to remember. Transformers strictly require an alternating current, or AC, supply to function. Why? Because alternating current is constantly reversing direction, and that constant shifting is what creates the changing magnetic fields needed to push power from one side to the other. Direct current, or DC, yeah, that simply won't work here.
Let's break that working principle down into 4 really logical steps. First off, an alternating current flows into the primary coil. Second, that current creates a fluctuating, alternating magnetic field right around the coil. Third, we use a ferromagnetic core, usually something like iron, to kind of grab and guide that magnetic field in a closed loop. And fourth, as that shifting magnetic field passes through a totally separate second coil, it induces a brand new voltage right there in the secondary coil. It's wild. The power basically jumps across the gap using nothing but magnetism.
Section 2, step up versus step down. Now that we get the physics, let's look at how we control the voltage. By simply changing the number of times we wrap the wire around the core, we can completely manipulate the power. A step-up transformer has way more turns of wire on its secondary coil than its primary. That boosts the voltage up and drops the current down, which is absolutely perfect for pushing power over really long distances. On the flip side, a step-down transformer has fewer turns on the secondary coil. That brings dangerous high voltage down to a much safer level and pushes the current up so our homes and appliances can actually use it. Oh, and quick side note, if both coils have the exact same number of turns, we call it an isolation transformer. It doesn't step the voltage up or down at all, it just isolates a specific circuit for safety.
And to put this into perspective, just look at the sheer massive scale of real-world power transformers. These absolute giants are used right at the generation sites to step up voltage to crazy high levels, sometimes hundreds of thousands of volts. By doing that, the current drops dramatically, which practically eliminates the amount of energy lost as heat when the electricity travels through miles and miles of transmission cables.
Section 3, anatomy of an oil-immersed transformer. Transformers can be classified by how they're cooled, like dry-type transformers that rely purely on circulating air, or heavy-duty oil-immersed ones. Let's do a virtual teardown of a real-world oil-immersed transformer. To make this super easy to remember, we're going to compare its physical parts to the vital organs of a living body. First up, we have the heart, the core, and the windings. The core acts as the magnetic pathway, but it is never just one solid block of iron. If it were, stray electrical currents, called eddy currents, would swirl around inside and generate massive amounts of heat. Instead, the core is built from ultra-thin, laminated sheets of silicon steel. Now, in what we call a core-type transformer, the windings wrap around these core limbs. In a shell-type design, the core essentially wraps around the outer edges of the windings to give it more physical protection. Either way, those primary and secondary copper windings are separated by insulating paper and securely suspended right inside the main tank.
Next, let's look at the conservator tank. If the core is the heart, the highly refined mineral oil filling the main tank is definitely the blood. It insulates the electrical components and absorbs heat. But when the transformer is working really hard under heavy loads, that oil gets hot and physically expands. If the main tank was completely sealed, it would literally burst. So an expansion tank called the conservator is mounted on top. It's intentionally kept only half full, which gives the hot oil a safe, empty space to expand into.
As that oil level naturally rises and falls in the conservator tank, the transformer basically has to breathe air in and out. But we definitely can't let dirty, moist outside air touch the oil. Enter the breather, the lungs of our machine. When air gets pulled in, it first passes through a small cup of oil at the bottom, which traps solid dust particles. Then, the air passes through silica gel crystals, which completely absorb any moisture. This brilliant setup ensures that only perfectly dry, pure air ever enters the tank.
We also have some essential safety and cooling mechanisms to talk about. The Buchholz relay is this incredibly clever gas-actuated safety switch located between the main and conservator tanks. If an internal fault happens and the oil starts to burn and release gas, this relay catches it and trips the circuit breaker before a disaster happens. There's also an explosion vent, which is just a purposely weak metallic pipe that blows out to release extreme pressure if things go completely wrong. Finally, the radiator fins on the outside act a lot like the skin, using outside air to cool the hot oil as it cycles through them.
Section 4. Efficiency and losses.
As incredible as this anatomy is, we do have to talk about where energy goes. Because, let's face it, no machine in the physical universe is 100% perfect, and transformers are no exception. Energy is always lost along the way. So the crucial point here is understanding exactly how that energy is lost. First, we have iron or core losses. This includes those eddy currents we just discussed, plus hysteresis loss, which happens when the magnetic field is constantly flipping back and forth. Then there's copper loss, which is simply the heat generated by the natural resistance of the copper wire itself. We also have dielectric loss from the insulation materials slightly resisting the flow. And fascinatingly, there's magnetostriction. You know, if you've ever stood near a transformer and heard that loud, constant humming sound, that is actual energy being lost as sound waves because the magnetic field is literally causing the metal core to vibrate.
Because of all these inevitable heat and power losses, standard engineering practice dictates a golden rule, the 80% maximum loading rule. When you're sizing a transformer for a building or a neighborhood, you should never ever plan to run it past 80% of its maximum capacity. That remaining 20% buffer is absolutely vital to ensure the stability, safety, and long-term lifespan of the machine.
Section 5. The big picture. Let's zoom out from the individual transformer and see how it fits into the massive, interconnected web of the electrical grid. Just look at this entire journey. Electricity is generated, stepped up to extreme voltages for long transmission, and then arrives at primary substations. Here, large step-down transformers drop the voltage to medium levels. Along the whole way, grid operators rely on specialized instrument transformers, like current transformers, CTs, and potential transformers, PTs, to safely step down and measure these extreme currents and voltages for monitoring purposes. The power then travels further into our cities where smaller distribution transformers step it down one last time, to the 120 or 240 volts that we can safely plug our laptops and refrigerators into. It is just a continuous, cascading flow of energy control.
But you can't just connect a wildly expensive transformer directly to the main power lines without any protection. That is where the ring main unit, or RMU, comes in. Think of the RMU as the ultimate bodyguard for the distribution transformer. It's a highly secure, metal-enclosed switchgear that sits right next to the transformer. It houses disconnect switches and a circuit breaker, allowing engineers to safely isolate the transformer from the grid if there's a fault, or just for routine maintenance.
And this brings us to the beauty of the ring network. In older, radial networks, power flowed in one single direction. If a cable broke, well, everyone downstream went dark. But modern grids use ring networks. Because RMUs have multiple switches, they can accept power from two entirely different directions. If a cable gets cut on the left side of your neighborhood, the RMU simply switches to pull power from the right side. It provides this crucial redundancy, ensuring your lights actually stay on even during a local fault. Wow, what an incredible journey, from basic physics all the way to neighborhood grid reliability. Let's quickly summarize our key takeaways. We learned that transformers manipulate AC voltage using electromagnetic induction. We use step-up models for efficient transmission, step-down models for safe use, and isolation models for circuit safety. We saw how laminated silicon steel in core-type and shell-type designs prevents massive energy loss, and how the oil, conservator tank, and breather are vital organs keeping oil-immersed machines perfectly cooled. Finally, we saw how ring main units act as bodyguards, securely integrating these transformers into highly reliable grid loops.
Which leaves us with a pretty massive question. As our global energy demands continue to absolutely skyrocket with electric vehicles and huge data centers, how will the physical and efficiency limits of these silent grid workhorses adapt to power our future? It's a fascinating engineering challenge that's unfolding right now.
If you found this breakdown valuable and want to keep mastering the systems that power our world, please make sure to like, share, and subscribe to the channel for more explainers just like this one. Thanks so much for watching and keep learning.